はい、お願いします。はい。はい。始めていいのかな。SD ですか。Okay, this is from JAXA. Can you hear me? So today I'm going to talk about the Hayabusa and Hayabusa 2. I'm Makoto Yoshikawa. I'm working in JAXA, and I'm very happy to talk about the Hayabusa and Hayabusa 2 today. So now in this slide, there are two figures. Left one is the original Hayabusa, and the right one is Hayabusa 2. Okay, so today I'm going to talk about both of these missions. Okay, this view graph shows the lunar and planetary missions of Japan. Japan launched these satellite and spacecraft. The starting mission were Sakigake and Suisei. They approached to Comet Halley in 1985. And then we launched Hiten to the moon. We had an experiment of swing by Hiten. And then 1998 we launched Nozomi, Mars Explorer. And then 2003 we launched Hayabusa. Today I'm going to talk about in detail about this. And then we launched Kaguya 2007. It was rather big spacecraft, and we took lots of data from the moon. And next mission were Akatsuki and Icarus. Akatsuki went to the Venus. And Icarus, it is a solar sail mission. And now we are operating Hayabusa 2. Yes, I will talk about this in detail today. Okay, so next slide. I show the Japan's asteroid explorations. The starting point was 1985. At that time, we had a small meeting to discuss about the sample return mission from Asteroid. And we had Hayabusa from 2003 to 2010. Yes, and then now we are operating Hayabusa 2. And for the future mission, we are discussing several missions. One is Jupiter Terran mission by large solar sail, and the other one is, for example, Phaeton mission by small spacecraft. Anyway, JAXA want to investigate these small bodies. And this slide shows the technology of sample return. We developed many new technologies for Hayabusa. For example, ion engine, autonomous navigation, sample collection system, and reentry capsule. And for Hayabusa 2, we have developed impactor system, K-band communication system, etc. And of course, the purpose of these missions are science. We want to know the origin and evolution of the solar system. We want to study planetesimal formation, evolution from planetesimal to asteroid, and initial material circulation in early solar system, relation between asteroid and meteoroid. So that's why we launched Hayabusa and Hayabusa 2. The target of Hayabusa was Itokawa, and we studied Itokawa in detail. And the target of Hayabusa 2 is Ryugu. These two asteroids are different. Itokawa is S-type, and Ryugu is C-type. So by Hayabusa 2, we would like to study C-type asteroid, which will have the organic matters and water. This slide shows the history of Hayabusa and Hayabusa 2. We have a rather long history. The starting point was the project of Hayabusa started in 1996. At that time, we call Muse C. And then Hayabusa was launched in 2003. And it arrived at Itokawa 2005. But at that time, we had a serious problem. So, yes, so at 2005, at the end of 2005, we thought that Hayabusa could not come back to the Earth. So that's why we proposed Hayabusa 2 mission. Originally, we are discussing post-Muse C mission, which is much advanced mission. But since Hayabusa had a trouble, we proposed Hayabusa 2 as a revenge of Hayabusa. But anyway, Hayabusa were able to come back to the Earth 2010, and we can get the surface material of Itokawa. But Hayabusa 2 project was approved after Hayabusa came back to the Earth, and Hayabusa 2 project started 2011, and it was launched 2014, and it will arrive at Ryugu next year, just 1 year from now. Okay, so this shows the Hayabusa spacecraft. This is a model of Hayabusa in real size. We put this model in ISAS, where I am working. So you can see the size of spacecraft. It is not so big, and the size of body is about 1 meter and 1.5 meters. So it is rather small as the interplanetary spacecraft. And this is Itokawa. The reason why we name Hayabusa is like this. Hayabusa means falcon in Japanese, and Itokawa comes from the famous person who is Hideo Itokawa, who is the father of modern Japanese rocketry. And Muse C is a code name of Japan's engineering mission, Mu Space engineering spacecraft. So, and the C is the third spacecraft. So that's why we call Muse C. And after successful launch, we rename it Hayabusa. Okay, and this is a mission scenario. Hayabusa was launched in 2003, and just about 1 year later, it came back to the Earth to perform Earth swingby. And Hayabusa arrived at Itokawa in 2005, and it stays only 3 months. It make 2 touchdowns, but first touchdown was failure. It was the emergency landing, and second touchdown was okay. But after the second touchdown, we had several very serious problems. But we were able to overcome such a serious problem, and Hayabusa came back to the Earth 2010. Now I show you computer graphics of Hayabusa mission. So Hayabusa was launched like this, and then solar paddle was deployed like this. And this is the sampler horn. And yes, this is the IMO engine, and Hayabusa left from the Earth. And first 1 year, it moved like this, following the Earth. And 1 year later, it approached to the Earth. This is the Earth swingby. Yes, and the orbit changed to the orbit of Itokawa and approached to Itokawa. And September of 2005, Hayabusa arrived at Itokawa. Yes, so at first, Hayabusa observed Itokawa carefully. It measures the distance. This is a red line shows the LiDAR measuring the distance, and we took lots of photo and make a shape model, and we decide where to touch down. But before touching down, we release a target marker. And looking at the target marker, Hayabusa spacecraft going down to the surface like this. And before touching down, it released a small rover and touched down. And when it touched the surface, a small projectile was released like this, and fragments going up. And we got the surface material, but unfortunately the projectile was not fired. So this is a Minerva small lander, but we failed to put down on the surface of asteroid. So after this, Hayabusa came back to the Earth, and it released the re-entry capsule, and capsule landed on the desert of Australia like this. So this is a whole mission scenario. Okay, so this is a photo when Hayabusa re-entry to the Earth. This is a very beautiful photo, and you can see two lines. The line below is by capsule, and the very bright one, it is spacecraft itself. It burned in the atmosphere. And this is explanation. So you can see the height change from 100 kilometers to 40 kilometers like this. Okay, so this is a Hayabusa spacecraft. As I said before, it is not so big. The mass, dry mass, is about 308 kilogram, and wet mass is just 500 kilogram. So it has an ion engine like this. It used the ionized xenon to accelerate spacecraft. The thrust level is not big, but it can work long time to change the orbit of Hayabusa. And this is another new thing, target marker. Target marker is artificial landmark. So it must be released before Hayabusa touch down to the surface. So it must not bounce on the surface. So it has small particles inside. Then when target marker hits the surface of Itokawa, it does not bounce. Yes. And this is a small rover, Minerva. It is very small, just 600 gram, 10 centimeters in the length. But it has 3 cameras, and it can even move. It can move. It can hop by using the small weight inside. There is a motor, and the weight is rotated by motor. Then Minerva body can hop on the surface of asteroid. But unfortunately, we failed to put it on the surface. When we released Minerva, the spacecraft velocity was a little bit exceed the escape velocity. So Minerva could not reach to the surface of asteroid. It was a very pity. And this is a sampler horn. We use a projectile to get the surface material like this. Okay, so these are the remote sensing instruments of Hayabusa. There are 4 instruments. One is CCD camera, Amica. The next one is LiDAR to measure the distance between asteroids and spacecraft. And then we have NIRS, near infrared spectrometer, and finally we have X-ray fluorescence spectrometer, XRS. So these are instruments for Hayabusa, but Hayabusa 2 also has a similar instruments. I will talk about it later. And this is engineering of Hayabusa. We had many challenges. After launch, there was a Earth swing-by, and Earth swing-by was successful. And then we had solar conjunction. And before arriving at Itokawa, we used optical navigation. It worked quite well. And we were able to reach to very small asteroid Itokawa. And after touching down, spacecraft came back to the Earth, and the re-entry capsule was released. So this is a re-entry capsule landed on the surface of the desert of Australia. And after bring it back to Japan, we opened the capsule, but we cannot find grains by naked eye because we could not shoot the projectile, but we can find lots of small particles inside of the capsule. So we pick up small particles, and the particle is like this. Okay, so this is a particle by scanning electron microscope. The size is just 100 micron, 0.1 millimeter, very small, but we can analyze such small particles. And even we can cut the particle like this. So now we know lots of things by studying these small particles from Itokawa. And I want to talk about one more thing for Hayabusa. We have many difficulties like this. For example, before arriving at Itokawa, 2 reaction wheels were broken. There were 3 reaction wheels, so only one was survived. And after second touchdown, much more serious problem occurred. For example, fuel leak or communication shutdown, and finally we cannot use the chemical engine. But we were able to overcome these difficulties. And finally, just a half year before coming back to the Earth, all IMO engines were broken. But again, we can overcome this difficulty, and Hayabusa came back to the Earth 2010. Okay, and this is a Itokawa, very strange looking asteroid. Here I have a model of Itokawa, this one. This is a very precise shape model. The size is 1 to 2,000. So a real Itokawa is 2,000 larger than this one. And now we know lots of information about this strange looking object. Okay, so yes, so we know a lot of things about Itokawa, and the most important thing is the structure of Itokawa. So this is not a single body. We found that this is the structure of Itokawa is rubble pile. So lots of small fragments get together and formed Itokawa. And also from the sample, we know lots of things. For example, the original body, planetesimal, the size of planetesimal may be larger than 20 kilometers in diameter. This is one of the important result from the sample of Itokawa. And such result were published in Science Journal in 2006 and 2011. And also in Japan, Hayabusa was very popular, and there are 3 movies for Hayabusa. These 3 movies are very interesting. Of course, it based on the stories of Hayabusa, and also many public people supported Hayabusa mission, and they send us lots of things to us. Okay, so what we have learned from Hayabusa? Of course, we have learned science and technology, but in addition to these, we learned, for example, the excitement of challenge to the world's first, or the difficulty of the world's first. Yes, we know that it is very difficult to do the thing that is first thing in the world, and we think that it is very important to do such work, because we can have many young people to this such a challenging mission. Now I move to Hayabusa 2 spacecraft. This photo shows the flight model just before launch. The size is again almost same as original Hayabusa, so not so big. And this shows the objectives, Hayabusa and Hayabusa 2. So Hayabusa was the technological demonstrator. So the main purpose is engineering. Of course, science is important, but main purpose was engineering. For Hayabusa 2, the main purpose is science. We want to study origin and evolution of the solar system, and we want to study especially organic matter and water. And of course, engineering is important for Hayabusa 2. And since Hayabusa had lots of troubles, so we improved many parts in Hayabusa 2. So actually, up to now, Hayabusa 2 is working quite well. And main difference between Hayabusa and Hayabusa 2 is the target. Itokawa is S-type asteroid, but the target of Hayabusa 2, that is Ryugu, is a C-type asteroid. This is very important thing. So now I show you this chart. This shows the spectral type of asteroids. So we have S-type groups and C-type groups and D-type groups. So since Hayabusa studied S-type group, so next target should be C-type. So that's why we chose Ryugu as the target of Hayabusa 2. Okay, so now I show you the mission scenario of Hayabusa 2. So the launch was December 3rd, 2014, and just 1 year later, December 3rd, 2015, Hayabusa 2 came back to the Earth to perform Earth Swing-by. This is the same as original Hayabusa. And now Hayabusa 2 is approaching to Ryugu, but we need still about 1 year to arrive at Ryugu. So Ryugu arrival is June or July 2018, next year. So about 1 year from now. And this time Hayabusa 2 can stay near the asteroid about 1.5 years. So at first Hayabusa 2 will observe Ryugu in detail, and we will decide where to touch down. And Hayabusa 2 can touch down 3 times. So maybe we will try to touch down twice, and then we will do the new experiment, that is to create a small crater on the surface of the asteroid. And after creating small crater, if possible, Hayabusa 2 will touch down to this newly created crater to get the subsurface material. Hayabusa 2 will leave asteroid at the end of 2019, and about 1 year later, at the end of 2020, the capsule will come back to the Earth, and then sample analysis will be started. So this is a whole mission scenario. Now I show you a short movie of Hayabusa 2. Hayabusa 2 is now arriving at the asteroid Ryugu, and then this is the same. This is the target marker. It will be released before touchdown. So this is a quite similar way that Hayabusa did. And the sampler won't touch the surface, and a small projectile will be shot, and the fragments will go up to the capsule. So this is quite similar to Hayabusa. But from here we will do the new thing. Small box we call impactor will be released, and it will go down slowly, and then the spacecraft will quickly move to behind the asteroid. Then small impactor will explode like this, and we can make a small crater on the surface of asteroid. The size of crater may be about 2 or 3 meters in diameter, and if possible, we will try to get the subsurface material from the crater. This is very challenging, and it is very risky. Okay, so this is a missions movie. Now I explained about the Hayabusa 2 spacecraft. As I said before, the size is quite similar to original Hayabusa. So the size of body is about 1 meter by 1.6 meter, and the weight mass is about 600 kilogram. The difference between Hayabusa and Hayabusa 2 is high-end antenna. You can see there are 2 high-end antenna on Hayabusa 2. Original Hayabusa has just 1 high-end antenna. So Hayabusa 2, we will use 2 radio frequencies. One is X-band. Usually we use X-band, but Hayabusa 2 has K-band too. So if we use K-band, we can send lots of data than X-band. So when Hayabusa 2 arrives at the asteroid and get the data from asteroid Ryugu, we will try to use the K-band to download the data. So other parts, it looks quite similar to original Hayabusa, but actually we modified many parts, such as we modified ion engine, chemical thruster, and the reaction wheel, etc. And Hayabusa 2 has 4 small lander and rovers. One is mascot lander, which was provided by DLR and CNES. The mascot lander is about 10 kilogram weight, and it has 4 science instruments. And in addition to mascot, we have 3 small rovers, Minerva 2. The mass is about 1 or 2 kilogram, a very small one. This time we have 3 Minerva 2. And as for the science instrument, Hayabusa 2 also has 4 science instruments. One is ONCT. This is a CCD camera. Second one is LiDAR. So the ONCT and LiDAR is similar to Hayabusa, but we modified a little. And we have near-infrared spectrometer NIRS 3. This is different from original Hayabusa NIRS. NIRS 3 can detect 3 micron wavelengths. And finally, we have TIR, a thermal imager. This is a new thing for Hayabusa 2. So this slide shows the Hayabusa 2 has lots of separable payloads. Actually, Hayabusa 2 has 12 separable payloads. Reentry capsule, mascot, a small carrier impactor, 3 Minerva 2, and 5 target markers, and deployable camera. Yes, and this summarizes the remote sensing science instrument of Hayabusa 2. So as I said before, we have ONC, optical navigation camera. There are 2 kinds of ONC. One is ONCT, telescopic narrow angle camera, and the other one is ONCW. This is a wide angle camera. ONCT has 7 filters. And LiDAR, light detection and ranging. We modified LiDAR to adapt the low albedo of C-type asteroid. The range of measurement is from 30 meters to 25 kilometers. And NIRS 3, this is a near-infrared spectrometer. The wavelength ranges between 1.8 micron to 3.2 micron. And finally, thermal infrared imager, TIR, the wavelength ranges from 8 micron to 12 micron. Okay, so now I show you the movie of Hayabusa 2 remote sensing instruments. At first, ONC camera. There are 3 ONC, ONCT and 2 ONCW, W1 and W2. So ONCT has a filter wheel like this. And angle is about 6 degrees. This is a filter wavelength. Yes, next one is ONC W1 and W2. These are wide angle camera. So using these two cameras, we can see almost every part under the spacecraft. So these cameras are mainly used for the navigation, but it can take the science data too. So next one is NIRS 3, near infrared spectrometer. We will try to get the data related to water by using the NIRS 3. The view angle is very small, just about 1 degree. So we will scan the surface of asteroid. So third one is a thermal infrared imager. We will measure the temperature of the surface of asteroid. The temperature of the surface will be changed day and night. So we want to know how the temperature will change. Finally, a laser altimeter, LiDAR. So we measure the distance between the surface of asteroid to spacecraft. And if possible, we will try to measure the dust around the Ryugu. Okay, so these are science instruments. So as I said before, Hayabusa 2 has several new payloads. So one is this high gain antenna, K-band antenna, and we have already checked K-band communication, and it was successful. And Hayabusa 2 has another new one, is a new thing, that is the small cannon impactor and a deployable camera, DCAM-3. So when small cannon impactor is used, Hayabusa 2 spacecraft must be behind the asteroid. So Hayabusa 2 cannot see the impact events. So before Hayabusa 2 hides behind the asteroid, it will release a small camera. That is this one, deployable camera, DCAM-3. And this DCAM-3 can take the image of explosion and the crater, creating crater. And yes, so this is another improvements. One is the attitude control system. The other one is the propulsion system, ion engine. So these are also modified from Hayabusa. And the number of target marker was increased from 3 to 5. So Hayabusa 2 has 5 target markers. And this is a small change in sampling system. Both Hayabusa and Hayabusa 2 use the projectile to get the surface material. Projectile is shot to the surface, and it hits the surface, and the fragments will go up to the capsule. But Hayabusa 2 has another small things. On the tip of the horn, it has a small change, and fragments, I mean the surface material, will put on it, and we can correct it by this simple mechanism. The reentry capsule is basically same as original Hayabusa, but it has several measurement equipment inside of the capsule. This is a sampling operation sequence. The sequence is similar to original Hayabusa. So at first, a spacecraft goes down to the surface about 100 meters above the surface. Then their target marker will released. And after target marker stays on the surface, spacecraft will go down and touch down, and then lift off. And this sequence is similar to original Hayabusa, but this one, artificial crater generation operation, and this is a rather difficult one. So spacecraft will release the impactor, then it will hide behind the asteroids. But before hiding asteroids, a small camera was released, and this small camera, DCAM-3, will watch the impact event. So this sequence is quite complicated and risky. So we must do this sequence very carefully. Okay, so now I show you the launch of Hayabusa 2. It was December 3rd, 2014 by H2A rocket from Tanegashima Space Center.
All systems are ready. Main engine ignition. SRB ignition and liftoff.
Yes, it was a very beautiful launch.
Launch vehicle number 26 with the Hayabusa 2 and 3-second retrievals on board. Space Center at 1:22:04 p.m. on December 3, 2014, Japan Standard Time.
Okay, so after launch, we had a critical operation, and all of these critical operations were successful. And then this shows the orbit of Hayabusa 2. So after launch, first 1 year is first 1 year the orbit is quite similar to the orbit of the Earth, and then Earthing by in December 3rd, 2015. Then the orbit of Hayabusa 2 changed to the orbit of Ryugu, and we need 2 revolutions around the Sun, and Hayabusa 2 will arrive at the Ryugu June or July 2018. Yes, this is a very complicated data. This is what we did in the commissioning phase. We checked lots of payloads and instruments during the first 3 months after launch. And then this shows the regular operation up to the Earthing by. Sometimes we used IMO engine to control the orbit. And Earthing by was December 3rd, 2015. It looks like this. This shows the swing by orbit. So the nearest distance is about 3,000 kilometers from the surface of the Earth. Hayabusa 2 approached to the Earth from northern direction and went to the southern direction. And before and after the swing by, we took lots of images of the Earth and the Moon. So this shows the image of Earth by ONCW, a wide-angle camera, just before approaching to the Earth. So we can see the Earth quite clearly. And this shows the other images. We took a color image by ONCT or thermal image by TIR, and we took the spectral, near-infrared spectral data by News 3. And the experimental radar, this is a additional experiment. Radar were able to detect from the laser from the Earth-based station about 6 million yes. Sorry, sorry, I don't remember the distance, but very far from the Earth. Okay, so after this, this is an operation in 2016. After the Earthing by, the most important operation is the IO engine operation. There are 3 long-term IO engine operations. The first one is from March to May in 2016, and the second one is from December 2016 to April 2017. So both of these IO engine long-term operations were successful. And now, at present, we do not use IO engine. The spacecraft is just cruising to the asteroid. But still, we need one more long-term IO engine operation. It will be done January 2018, next year, to just arriving at the Ryugu, maybe May or June of 2018. Okay, now I talk about the target asteroid, Ryugu. From the ground-based observation, we had many data, and up to now, the estimated size is about 900 meters, so a little bit larger than Itokawa. But the shape is different. Itokawa is elongated shape, but Ryugu is probably not so elongated, but it is rather spherical. Here I have a small model of Ryugu, yes, and this is something like this, but we don't know exact shape. Maybe we will know this 1 year later. And the important thing is the Ryugu is a C-type asteroid, so the albedo is very low, about 0.05. Okay, and yes, this is a very easy understanding for the size of Itokawa and Ryugu. These two towers is in Japan, in Tokyo. So Ryugu is much larger than Itokawa, but still it is very small asteroid. So we will study Ryugu by using many science instruments, and we can study a wide scale range. So this slide shows our plan to study Ryugu using ONC camera, LiDAR, and News 3 TL. We will study large scale science, and then we have Mascot and Minerva 2 land and rover, so it can study centimeter scale science, and after getting the sample, we can study micron scale science. So by Hayabusa 2 we can do the wide science. Okay, so Hayabusa 2 has a large collaboration with international community. Of course, we are collaborating with USA, NASA, Europe, DL and CNES, and Australia, and we had a very good relationship between OSIRIS team. And now many Japanese people support Hayabusa 2 mission. They sent us these things, and yes, and the Hayabusa 2 project also do many outreach and educational activities. Okay, so this is Itokawa. So before arriving at Itokawa, we know only the shape we know was just like this. So, but after after Hayabusa arrived at the Itokawa, we know Itokawa is something like this. So now Hayabusa 2, the Ryugu is, we know Ryugu like this, but maybe 1 year later we will know exact Ryugu. So we are very just one year later we are very excited. We will be very excited to see Ryugu. Okay, so this is a final slide. These small bodies are very interesting in many reasons. Of course, we study science, the solar system science, and we can know the origin and the evolution of solar system. And also, these small bodies are important for the space guard or planetary defense, and it will have the resources, and these small body can be the target of manned mission. So there are lots of interesting things in small bodies. So that's why in JAXA we are studying such small bodies in the past and now and in future. Okay, thank you very much for your kind attention.